Peter, thank you so much for the invite. It's a pleasure and honor to be here speaking with you. I should give a disclaimer in advance. To the best of my knowledge, no solutions to Hilbert's 13th problem are going to be announced during the course of this seminar. If you want to surprise me, that's good. But there's a lot of rich mathematics in and around this problem that Benson and I and also Mark Kisson have been uncovering and building out. And so the goal of these talks is to sort of share for you the context and talk about some of the things that we can prove, even if we can't yet approach the 13th. Okay, so what I'm talking about today began as joint work with Benson, but he ultimately declined to be listed as a co-author on the paper. And it's taking place within the context of this larger ongoing joint work with Benson and Mark Kisson. Great. So the basic problem that we're asking about in this whole area is if you're handed a polynomial in terms of the coefficients, how do you find the roots? How do you understand how the roots depend, as you say, vary the coefficients or put some restrictions on them? And that problem's been around for a long time. The perspective that you see really emerging in the 18th and 19th century is you should view this as a problem about algebraic functions. So if you hand me some n-tuple of complex numbers, then I have a function which spits out all of the roots of the polynomial with those coefficients. And so it's a sort of multi-valued function in the AIs, and it's algebraic because the values are governed by some algebraic condition. And more generally, the AIs don't have to be complex numbers. They can be rational functions on a variety of your choice. And I figured it's sort of best to lead by example. And there's a quote by Felix Klein writing at the very beginning of his career in 1872. And he says, "The general theory of algebraic functions is most beautifully illustrated by a number of particular geometric examples, including the problem of finding flex points on a cubic curve, the 27 lines on a cubic surface." Here's sort of the real points of the surface rotating, so you can see it. The 28 bitangents on a planar quartic. So here, these four ovals are the real points of a particular quartic, and a bitangent is any line that's tangent at precisely two places. And you can see that 28 of those are these blue lines. And here we actually can visualize the close relationship between these two functions. Because if you hand me a cubic surface and I project from a point which is not on one of the 27 lines, the branch locus of that projection is a planar quartic. And all of the 27 lines go to bitangents, and I pick up the 28th from the exceptional locus. This is a sort of relationship between these functions that's been around for a long time. And finally, the last example Klein says, he says especially the construction of the regular polygons. So here's a sped up construction of the 17-gon, just to make Klein's point for us. And he goes on, he says, the great value of these examples lies in the fact that the conceptions of the theory, which are intrinsically abstract, are presented to the eye in a vivid way. This is one of the sort of the appeals of the subject for many people. All right, so let's get a sort of a proper definition so we know what we're talking about. I'm going to work throughout over a field of characteristic 0. And an algebraic function on a variety x is just a finite correspondence, a finite rational correspondence. So concretely, that means you have some branched cover, some quasi-finite generically tall map over x, and then you have a regular valued rational function on that. And the key datum in all of this, everything I'm talking about today, everything that Benson will be talking about tomorrow, is this branched cover. So we're really just going to focus on that as the kind of core object of an algebraic function. All right. And the types of things you want to do when nature hands you an algebraic function, historically and today, we want to do two things. One, you want to construct the simplest formula you can. And two, you want to sort of prove that no simpler formula is possible. You want to say, I've got the best solution right here, and then you want to be able to convince your friends that this really is the best solution. They couldn't do any better. And my focus today is on constructing formulas. So for constructions, we have a lot of tools from algebraic geometry, invariant theory, things like that. And that's what will be the sort of focus of the talk today. And sort of how Benson and I got into this, I think of myself as a topologist. And Hilbert sort of suggested that maybe we could use topology to obstruct formulas. And so that'll be the focus of Benson's talk tomorrow. And this paradigm of like, let's get the simplest and prove no simpler one, is possible, that's been around for a while, and it's sort of worth remembering that. So you can consider this universal quadratic right here, sort of a universal two-valued algebraic function. And then we have an old theorem, here the cuneiform tablets apparently containing the quadratic formula, where the Babylonians said if you allow us arithmetic and this single function of one variable, the square root, then we can write a formula. And a little later, Pythagoreans come along and say, you really need that square root. No simpler form is possible. So this is like the paradigm that the field has been trying to recover for a long time. Another well-known example, Abel's theorem in 1824, says there's no formula in radicals for the general quintic or higher degree n polynomial. Much less well-known is an earlier theorem of Bring, who proved that if you allow radicals and this Bring radical, this one variable function here, you can solve the general quintic. And Bring's writing this in 1786, and he sort of says, well, this is not quite a solution in radicals, but maybe this will get us closer, sort of optimistic. And by the time of Abel's theorem, we know that actually this is in some sense the simplest possible. All right. And Klein, writing on this at the first ICM, speaking on this at the first ICM at the end of the 19th century, said, formally the solution of an algebraic equation used to mean its solution by radicals. And even at the present time, such ideas are still sometimes prevailing. But ever since the year 1858, a very different point of view should have been adopted. That's still true in this sense. I mean, before I started working on this project, if you'd asked me what a solution of a polynomial was, I would have been, well, formula in radicals and quintics are unsolvable. But we have formulas from the classical literature, and Klein was sort of calling us to push beyond the solvable, unsolvable dichotomy. Like, what happens for degree 6? What happens for degree 7? All right. So examples of algebraic formulas, sort of I should give you a definition of that so we know what we're working with. I'm going to recast everything geometrically. It's my preferred way of thinking. You can do everything in fields if you want. We're doing birational geometry here. So this square root, this is a very nice function. You can encode it just as this branched cover of P1, just send z to its dth power. And that gives you the sort of radical. And from this perspective, you can say, OK, the Babylonians, what did they do geometrically? They took the space of quadratics, that's c squared. They sent it to its discriminant. They took a square root of that. That's this branched cover E1 right here. And now they have a polynomial map on that, which recovers this. Great. So this is, again, this is a formula. Here's a geometric portrait of the quadratic formula.
I think that was on the top.
Yeah, that's actually, yeah, that's I cleaned up the tech a little bit. So, OK. A little less simple is Klein's icosahedral formula for the quintic. So this is a spherical icosahedron borrowed from Nash. And we're going to construct two rational functions. So my first function, f, is just going to have its zeros at the 12 vertices of the icosahedron. And my next one, h, is going to have a 0 at the center of every face. So f is degree 12, h is degree 20. We want to make a single function out of those. So we're going to raise f. We're going to raise h to the third and f to the fifth to get a degree 60 formula. And then for good arithmetic reasons, we're going to put this denominator there. And this is the icosahedral function. So this is like radicals, but a little more complicated. All right. And Klein, in his lectures on icosahedron, you can summarize them by saying there's some 3 specified rational functions, some square roots of those. And if you allow me those square roots in the icosahedral function, I have a formula for every quintic. And geometrically, what's going on is it says, well, you've got the space of quintics here. OK, you've got this covariant a that he writes down. You take a square root. You have the discriminant of the quintic. You take a square root. And then you can push everything down to the icosahedron. And that will give you the quintic. Right, so there's some final dominant map, which I couldn't tech, from once you've adjoined the values of those functions, this E3, now you can write a formula for every quintic, like that. OK. And this is sort of the paradigm. So if we're saying, what is a formula for some algebraic function in terms of some other functions, well, it's going to be a tower of these branched covers. And each one of these branched covers is built up by pulling back along some rational map the specified branched cover for one of the functions that you chose right there. All right. And it's sort of a statement. This is a bit of a weird looking definition to modern eyes. It's unwieldy. It's challenging to work with. But every example in the classical literature follows this pattern. So it's sort of what nature hands us. And just to compare with Klein, So right, it's this tower. And here, you can just see that Klein's icosahedral formula is a sort of example of that paradigm. All right, questions?
So is there, like, can you characterize which kind of function in terms of Galois theory? Like, do you know?
Great question. Great question. So the whole challenge of this area, or much of the challenge, bifurcates on this notion of sort of natural rationalities and accessory ones. So natural ones are all the ones you can read off just by looking at the structure of the Galois group itself. But here for the quintic, once I've adjoined this square root of the discriminant, I just have A5. So there's no other normal subgroups of that whatsoever, as we know. And this square root here, I could have reversed the order. It doesn't make a difference here. Isn't something you can see naively at the level of the Galois group. It's what's called an accessory rationality. When you look at all quintics over the field where you would join that square root, the Galois group's still A5. It doesn't reduce that at all. But it does allow you to map that A5 onto the icosahedron. And you provably can't do that without this accessory square root. And this fact that you have to allow some finite list of unknown other functions in to possibly simplify it, that's like the main challenge. There's two main challenges. Birational geometry makes it subtle, but you could handle that if you didn't allow these accessory rationalities. Or if you said we can't divide, then you can handle the accessory rationalities. But the division plus this enlargement of the field, that's the whole difficulty.
But I think it's great. Kronecker, when he saw Klein do this, he said, "Oh my God, this doesn't use the Galois group. This is so unnatural." And Klein has this incredibly eloquent quote. And Klein proved that you needed this. You couldn't do it with just the Galois group. Looking at Galois groups, you needed these accessory, and he called it Kronecker's theorem.
Yeah.
And he says, like, you should be if you're faced with some phenomenon, you shouldn't run away and tear it. That's what God's given you. And you should,
He says it in quite short terms. Let me keep historical comments to a minimum. I'm already going to give you a bunch of context. And there's such a rich history. Part of what's amazing about this problem is that the history is like utterly unbelievable, with like major clashes of personalities by 19th century mathematicians who were comfortable expressing themselves in strong terms. So like the actual phrase Klein says is, are we to be men of science and face up to the phenomena that nature hands us, or are we going to hold on to our dogma and refuse to admit these new phenomena? And that's like one of like 5 quotes that one could talk about around this. Anyways, I'm happy to talk at length over beers about it. It's really pretty fun. Okay, this question of these things you can't naively see through Galois theory, that's a really subtle and important issue. So it's a great question. Okay, but the sort of where I was going with this, I gave you a definition of a formula. I give you an example of a formula conforming to that definition. And now you can just speak of this in shorthand. There's a formula for the general quintic in square roots and the icosahedral function. Great. Okay, so there are lots of other formulas coming for the classical literature. And Jordan and I believe Klein, though I can't pin Klein on this entirely, proved that if you hand me a cubic surface and an explicit choice of a line, I can write a formula for the remaining 26 lines using only radicals and the icosahedral function. And the best proof of this is this video by Steve Treadle, who's now at Stanford, where the construction is you've got your cubic surface, you have a line, you have a pencil of planes through that line. And so you can rotate that pencil. And of course, each plane in that pencil will intersect your surface in a cubic curve, but it'll be a singular curve since it has a line. So you get this pencil of conics. And if you look down here, you can see the blue is the conic that is being given by the intersection. And then you can do a computation, and you find this pencil degenerates at precisely 5 points. So at 5 points in this pencil, you get a degenerate conic, so 2 more lines, each of which lies on the cubic surface. So now you've got a quintic equation, because you have to find where this pencil degenerates. That's where some of your radicals and your icosahedron come on. And when you solve that quintic, you get 10 lines beyond your additional 1. And then now you can just do some easy Galois theory and see that once you have 3 disjoint lines, the Galois group, or the monodromy group, is solvable. So you then just adjoin some radicals, and you've got the rest. So This video, just sort of borrowing Benson's language, this video is probably a lower bound for my talk. Like, there's some argument that maybe I should just put this video on loop and we can think about it, and I can tell you about other details, but I'll play it once more. It gives you a sense of the way you can start using geometry to solve these algebraic functions. Great, and you're seeing the planes that are highlighted. Those are the singular ones. You can sort of see the singularities forming and unforming as it goes around. There you go. Questions on this at all? I should also say there's a really beautiful preprint that just came out where Benson and I taught a summer school at the University of Chicago. And Benson said, well, we know from Jordan and also Harris reproved it in the late 70s that if you have 3 disjoint lines, there's a formula in radicals for the rest. What's that formula? And it was recently sent a preprint by McKean and 2 others where they just do it, and they construct it very beautifully. I think it's on the archive now. So there's a lot of fun stuff to be done with this. All right. There we go. OK. Did I turn my clicker off? Great. OK. So I gave you some examples of algebraic formulas. And this begs the question, what do we mean by the simplest formula? And again, summarizing kind of what had been handed down over centuries, Klein said, look, at this point we mean the least number of variables in all the functions that we allow. So if we could solve everything in 1 variable functions, that would somehow be the ideal. Of course, we can do that up through degree 5. But if we can't, we'd like to know it, and we want to sort of see how much we can simplify the terms that have to show up in our formulas. OK, and again, let's formalize this into a sort of modern definition. If you hand me some branch cover, I can talk about its essential dimension. And the essential dimension is the least d for which I can rationally pull that cover back from a d-dimensional variety. So we can summarize this. It's a function of d variables after a rational change of coordinates. OK, and now that we know how to talk about sort of rewriting individual functions, we can now talk about the resolvent degree, which is about formulas. And it says the resolvent degree of phi is the least d for which there's a formula for phi in functions of d variables.
This definition we're saying was Brouwer and Arnold and Shimura in the 70s.
Yeah, this is formalized. So I mean, all these things in some sense are resolvent degree is kind of as old as the hills. It goes back. People are explicitly doing work on it as early as like 1683, I think, in Schernhaus. So it's been around for a while. This notion of essential dimension really comes out of Kroneker's work on the quintic in the 1850s, but it doesn't get formalized until like 98 by Buehler and Reichstein. So these ideas have been around for a while, but they sort of weren't brought into the modern corpus until quite recently. Interesting history there too. All right. So just for shorthand, I'm going to say Rd of n is the least d for which I can write a formula for the general degree n polynomial in d variable functions. We're just going to carry that through. And just some comments on how these two relate to each other. If you only allow 1 function in your formula, you're specializing to ED, to essential dimension. So if you allow formulas of some arbitrary finite length, you've got resolvent degree. If you only allow length 1, that's essential dimension. And there's a nice game you can play, and Benson will talk about this, where maybe I only want radicals up until the last stage, or maybe I only want some restricted class of functions. And you can sort of get intermediate invariance. And just to sort of compare these, so obviously, just from this observation, the essential dimension puts an upper bound on the resolvent degree. And the difference can be arbitrarily large. And a good example to keep in mind is here's a nice algebraic function. Just take some independent square roots and sum them. And the essential dimension is provably the number of square roots. But it's solvable in radicals. So the resolvent degree is 1, and the difference, just pick a big n. We have a lot of techniques for putting lower bounds on essential dimension. This restriction of only allowing 1 function, of not allowing any accessory rationalities, is very, very strong. So there's still a lot that we don't know there, a lot that we don't know. But we have a lot of techniques for at least putting lower bounds on the complexity, non-trivial ones. There's not a single known non-trivial lower bound for resolvent degree. For all we know, every algebraic function in nature, in existence, is solvable in 1 variable functions. Like we don't know. I believe that's not the case. I've got friends who are in print saying, yes, it is the case, and then deducing, Zinoviev, Reichstein, and some collaborators deduced, and Gillet and Chernisov deduced some recent conjectures of Bogomolov, assuming this strong form of Hilbert being wrong. So it's open, right? And I think that's pretty enticing.
The opposite has got the same conclusion.
Yeah, well, that would be right. I haven't tried seeing if I can deduce it that way. Okay, so right, we don't have any single lower bounds, and that's like really the sort of, anything like this. Any single example of an algebraic function that provably had resolved in degree 2 or greater would be a major advance, in my opinion. Yeah, I mean, it might be like P equals MP. I mean, possibly. I gave a talk on this in San Diego and could lie. I was like, this feels a lot like geometric complexity theory, so maybe there's something there, but I haven't been able to pin it down. From my optimistic perspective, you might say we're somewhere where math was in like the 18th century, where people tried for centuries to find formulas and radicals for the quintic, but they couldn't prove that it was impossible. And like, under this telling, maybe in a few decades, or hopefully sooner, we'll learn why. But we don't know right now.
Can you characterize those of essential degree 1?
Yes, that's classified.
And the Galois group they give?
Yeah, absolutely. So there's a lot of work, most notably by Alex Duncan. You can classify groups of essential dimension up to 3. And the list is basically what you'd expect by looking at the finite Mobius groups in those dimensions. You're using the classification. ED1 is pretty easy. It's Leroy's theorem and Klein's classification of Mobius groups. So A5 doesn't have essential dimension 1, as Klein proved, but all the cyclic groups do, and I think the dihedral groups as well. For 2 and 3, you're using the classification surfaces, or more recently, Prokhorov's classification of rationally connected threefolds. You can sort of read it off on that. But that's a bad method for generalizing to higher degrees, right? We don't have a classification of fourfolds, so we can't say anything about ED4 right now. And this might take a while if that's your approach to try to build up the ladder. Other questions? Okay. Yeah, so ED of n goes to infinity if at least as quickly as n over 2. I mean, the current known values all conform to n minus 3, which is kind of what you'd expect by looking at like the moduli of marked points in P1. Somehow that should be the rigid object for it. But the best that we can prove right now is n over 2. Yeah. Benson and I conjectured, but we only made that conjecture because it seemed implicit in the literature for so long, someone needed to record it, that we believe that RD goes to infinity with n. But again, it could just be the constant function 1, so we don't know. All right. But having sort of introduced this invariant, we can now summarize a lot of classical results. So the various formulas for low-degree polynomials in radicals, that gives you that RD of n is 1 for n at least 4. We can summarize bringing Klein's work on the quintic, saying resolvent degree is 1 for there. And then sort of want to tell you about Hamilton's work. So Hamilton said if you have radicals, then every section can be solved using this particular 2-variable algebraic function. And he also did that for degree 7 with that 3-variable function, and for degree 8 with that 4-variable one. And so you can summarize this as saying that once n is at least 5, you at most need n minus 4 variables to write a formula. And at the end of the 19th century, Hilbert, surveying what was known and what had been accomplished, included this as his 13th problem. So in Paris, in the Universal Exposition, he gives this lecture on his 23 problems for the future of mathematics. He actually only gives 10 in Paris. This is one of them. So it's sort of interesting to look at which 10 he spoke on publicly in that setting. And in the sort of contemporary English translation, I just took the exact notation from 1900. That's why you have this weird F. But it's a quote. He says, prove that this equation of 7th degree is not solvable with the help of any continuous functions of only 2 arguments. And it's worth noting this is Hamilton's degree 7. So Hilbert's taking Hamilton's normal form and saying Hamilton has the best possible version, and actually there should be a topological obstruction, right? Poincaré had just invented algebraic topology 5 years earlier. You can read Hilbert as sort of throwing down a gauntlet and saying, great, you said it would do a lot of stuff. How about this? All right. And then at the end of his career, Hilbert returns to this. He has a beautiful paper, which should be better known, called On the Equation of Ninth Degree. And there he explicitly conjectures that Hamilton's normal form for the sextic is the best. So he says the resultant degree of the RD of 6 is 2. And then coming to the degree 7, he says, in my Paris lectures, I've already conjectured that it's not solvable even with continuous functions. So I can pass over that one. This should definitely be the simplest. He gets degree 8. He said, OK, Hamilton's bound is sharp there. And then interestingly, for degree 9, he gives a beautiful argument for how you can use the lines on a cubic surface to write a 4-variable formula for the degree 9. And this sort of making sense of this is kind of where the results I'm going to tell you about today kind of comes out of. I think it's a very cool idea. OK. But these are like sort of how the defining problems in the area. All right. So goals for today. I want to understand the geometry underlying these Hamilton-Hilbert normal forms. There's some very rich varieties that show up in the process of writing down these formulas, and it's worth kind of explaining where they come from. But this all takes place in the context of a problem first formulated by Segre, Beniamino Segre, and he said, can we just understand like how this number grows as n gets large? And so this is sort of a contribution to that, where we can at least put upper bounds on the rate of growth. All right. I said I'd comment a bit about the history. Sylvester and Hammond took up this problem in the late 1880s. And Sylvester actually had a sidelight as a lyric poet. He gave lectures on lyric poetry, and you can sort of see that in his prose styling. And he writes, the theory has been a plant of slow growth. The Lund thesis of 1786, Hamilton's report in 1836, and Sylvester's paper from the previous year constitute a complete bibliography up to the present day as far as they're aware. Klein's writing on this at the time, so they're not sort of in contact with Klein. But you can say, OK, let's try to add to this and say what gets us up to the present. And you've got Klein in his school. There's a lot of work, quite rich in there. Hilbert's paper in 1927. Wiemann has a paper in the same year. And then Segre works on this in the late 40s and 50s. Chebetarov's son, Gregory Nikolaevich, not Nikolai Grigorovich, has a paper in Nikolai Grigorovich also works on this. It's the subject of his ICM talk in 1932. But he doesn't work on upper bounds. He's trying to find an obstruction to simpler formulas. So anyways, his son picks this up. And then Brouwer gets to it in 1975. And it's worth noting that when we started working on this, Benson just comes in one day and he's like, I found this paper by Brouwer. It's got 0 citations. I don't know where you got it on Google Scholar or whatever. But it had been kind of completely forgotten. And this is the whole bibliography. I mean, I have a preprint on my website, so I'll tell you about that. But up to 2 years ago, this is it. And it's worth also noting that there are fatal gaps in 3 of these papers. So this gap, I'll tell you about the repair for it today. This gap can also be repaired, but I haven't gotten to the bottom of what that gets you. This is essentially the same gap as earlier, but I haven't sort of looked at that. So there's a lot of ideas, but not as many theorems as there should be, and I think that's kind of enticing. OK, so let's sort of talk about what's known. So Hamilton, in broad strokes, proves that actually this difference, the number of variables you can get rid of to write a formula for the degree in polynomial, that goes arbitrarily large. And he computes the initial values of his function. How big does the degree have to be for me to get rid of our variables? And these are the numbers he gets. These you can find these in the online Encyclopedia of Integer Sequences, the Hamilton numbers. And you can see they grow pretty quickly, right? Your ability to do improvements falls off quite rapidly. But that's sort of where things stand. Sylvester and Hammond, among other things, wrote a generating function for this. And Klein sort of takes up the challenge. He says, look, there's a lot of math in the second half of the 19th century. Let's throw everything we have at it. And he brings in lots of different areas of math. So here, this sort of three-dimensional geometry uses symmetries of the icosahedron to write his formula. You can rephrase that as using exceptional isomorphism Lie groups. He then does that explicitly. I think he constructs this exceptional isomorphism to write a three-variable formula for degree 7. Uses this Valentino representation to write a two-variable formula for degree 6. So with a lot of hard work from invariant theory and algebraic geometry, he reproduces Hamilton's bounds, and then it taps out. Just to sort of tell you a little more about what Hilbert did, sort of foreshadowing for later in the talk. So Hamilton says you can get rid of 4 variables. In Hilbert's paper, he says, as a theorem, the 27 lines on a cubic surface.
Wait a minute. Sylvester has obviously an interesting idea because he's saying that you can find more and more coincidences. That
Yes.
function h is arbitrary to infinity, right?
I think Hamilton had proved that.
But who had started that?
Who?
I can see that if you're looking at small degree, that will, of course, permeate the higher degree.
Mhm.
The fact that, it's Hamilton.
Yeah.
Sorry.
Yeah. So Hamilton doesn't.
Sylvester.
Yeah, Hamilton's not explicit about it. Yeah. Sylvester gets you a lot.
He has discovered something in high dimension that's interesting.
Yeah. It's hard to read the Hamilton paper. It's really, but he is clearly articulating a general method that will get better and better as the degree is larger. All right.
Which, in other words, is not dependent on accidental isomorphism.
No, no. I mean, in modern language, what he's using is that if you let the dimension of projective space get really big, then low-degree hypersurfaces look a lot more like rational varieties. And so you can start finding solvable points, or I think he's basically only doing solvable points, but that's sort of what's going on. Okay. And then Peter surface is a good issue here. A lot of the math involved in constructing formulas, you can rephrase it as finding special points on projective varieties. And most of the literature on special points is on rational points. There's a very little bit of literature on solvable points. But for the question of formulas, we just care about, can you construct the point using only functions of d variables or fewer? So you have a lot more moves. And Hilbert's pointed out that, hey, maybe one move is just to use the 27 lines on a cubic surface. Heuristically, that's a 4-variable function. There's a 4-variable moduli space of smooth cubic surfaces. So if I could just leverage that on a particular cubic, I get a 4-variable formula, and then I'd have another 4-variable function I need, and so I'd have a 4-variable formula. And as Dixmuir points out, Hilbert's argument has a bunch of gaps. The most notable one is he just assumed that the cubic surfaces that he constructs are generic, and you can write down the equations explicitly, and they're manifestly not. So you have to do some work to show that you actually do get a map to moduli space, or you do, in Hilbert's language, have a pentahedral form. And that sort of All right, so what I was saying is this A is telling you that this is the parameter space for polynomials by their coefficients. This B is thinking of as the parameter space for Schoenhaus transformations. And so if I take a polynomial and a Schoenhaus transformation, I can spit out the transformed polynomial. Yeah. Other questions? Great, OK. Good. So now we've got this Schoenhaus transformations, and we start looking at interesting hypersurfaces in the space of polynomials. For instance, we can say, like, look at all polynomials where the first coefficient vanishes, right? Or any polynomial condition you want. But these are the ones I'll sort of look at, and I'll projectivize them because you can always rescale to get a simpler formula. OK, so I have these Schoenhaus hypersurfaces, and these are sort of interesting objects. You can write them; they're formulas. You have some infinite family. And you can also intersect them. So if I want to find a transformation that kills, say, the first n minus d minus 1 coefficients of a degree n polynomial, well, I better find a Schoenhaus transformation that lives on that complete intersection. Right? So these are the sort of Schoenhaus complete intersections. And this is sort of, the paradigm here is how do we show that the resolvent degree is at most d? One way to do it is to find a nice kind of multisection of this family of complete intersections here. And it's sort of worth commenting that if you want to restate this sort of field theoretically, we have this complete intersection, and we can just restrict it to the generic point of the base. So this is now some complete intersection defined over a function field. And we're trying to find special points of this. So if I just pass to function fields, this is just now some branch cover, some finite extension of the function field. And I want to find a point of this complete intersection on that. So if you can find rational points, everything's great. That's really a nice thing to do. But solvable points are just as good as rational from the perspective of resolvent degree. And I have a lot more flexibility in that. And again, I sort of think of myself as a topologist by training. I'd be very interested if there are people in the audience who are interested in this and think about things like rational points or solvable points on projective varieties. Like, come talk to me. I've done a lot of searching in the literature, and there doesn't seem to be a lot that I can directly apply, mainly because there's the work of Wiles, but a lot of stuff is for number fields. And so moving it to function fields should be easier, but it's sparser. So let me just advertise that. I'd really be interested in talking to people about it. Anyways, this is what you're trying to do. And if you can sort of say, well, this special point doesn't involve a function of more than d variables, oh, and then I've killed d variables with my Schoenhaus transformation, now I'm done. OK. And once you have this paradigm, Brouwer's observation, his proof is very simple. A complete intersection of degree r factorial has a dense collection of points of degree r factorial over the base field. So that's exactly where his bounds are coming from. And Hamilton's, at least the first step in Hamilton, can also be explained pretty simply. So the quadric that I'm always going to have in mind will be this Schoenhaus quadric that kills the first two coefficients. And Hamilton said, well, look, they have large linear subspaces, large isotropics, lots of them. And to write down an isotropic on a quadric, you just need to introduce some square roots. So with radicals, we can now pick some big isotropic on T1, 2. So pick some linear subspace there. And then you can intersect that linear subspace with your other complete intersection. And now you have a whole collection of points of degree r factorial over 2. And that just cuts Brouwer's bounds in half. Then he sort of keeps doing some version of this. OK. Then Hilbert says, OK, cubic surfaces have lines, and smooth cubic surfaces form a 4-dimensional moduli space. So what you'd like to do is you'd say, well, I have this Schoenhaus quadric. I just pick some 3-dimensional isotropic. And that's where you need n to be at least 9. You're not going to have a 3-dimensional isotropic unless your quadric is at least a 6-fold. But once you've got that, you can get a cubic surface just by intersecting with the next one. If your cubic surface determines a map to moduli space, now you have a 4-variable function that allows you to pick a line. Then you intersect that with the next one. Now you're solving a quartic polynomial in one variable. That's solved on radicals. And it's worth commenting, there's actually some issues where you have to check that your line is not twisted. And so that's another gap in Hilbert's. But recursive-Suslin's theorem does a lot of work for us, and it says actually throw in some more radicals and you can untwist every projective variety. And so that is sort of not a major issue. And this is how you get the 4-variable formula. OK, so the sort of main geometric contribution in my preprint is I can't prove that all these Schernhaus complete intersections are generically smooth. I'd like to. It's hard. It's really hard in practice to take an infinite family of hypersurfaces even and just prove that they're all, an infinite list of families of hypersurfaces and prove that they're generically smooth. I mean, you get into this and you're like, OK, there's a discriminant, so I'll just compute the discriminant explicitly. But that's a bad idea because it grows, the degree of the discriminant and the number of terms in it grows really, really quickly in the degree of the hypersurface and the number of variables. And so I'm also interested if there are more tricks. I'd sort of conjecture that the Schernhaus complete intersections, not just these ones where I had to have some condition on the 3rd degree, but like all of them are probably generically smooth. But that's more than I can prove right now, and it's more than I needed. So this is what you get. And I should comment on this. The way I showed is pretty elementary. You write these all out actually as integral families of complete intersections. And then you reduce them out a good prime and do some tricks with Frobenius, and you can show that it's smooth at that one fiber, therefore it has to be generically smooth. So you're sort of good to go. All right, and the sort of point of this theorem is that this fixes the main gap identified by Dixmier. So now we know that even though Hilbert's cubic is really non-generic, it's still smooth. So you can get a map to moduli space, or it's still generically smooth. Cool. OK, so wrapping up, you've got this geometric input that says you can get to moduli space when you need to get the improvements. And then there's a theorem from about 10 years ago by Waldron, building on work of Hochster and Laxov, which said that actually based on dimension count, every time you expect a linear subspace to exist, it will, for any hypersurface whatsoever. Right. And then you take this idea of how to use these nested sequences of linear subspaces, use the generic smoothness to cut down the number of variables of the functions you need to do to pick the linear ones, then use existence, recursive-Suslin, you get the new bounds. OK. Any questions? This is basically, I have one more slide in my talk. So. All right. Great, so that's the proof. So that was a lot to try to cover, I guess, in the last 10 minutes. But let me just end with another quote from Sylvester and Hammond, which I like quite a bit. And writing at the end of their paper, having done some work on it, they say the study of resolvent degree, far from being exhausted, has, in leaving our hands, little more than reached its first stage, and is believed will furnish a plentiful aftermath to those who may feel hereafter inclined to pursue to the end the thorny path which we've here contented ourselves with indicating, which lies so remote from the beaten track of research and offers us an example and suggestion of infinite series wholly unlike any which have previously engaged the attention of mathematicians. That's basically still true today. So hopefully we're trying to popularize this and get more people to join us to sort of put this quote to rest. But thank you.